What if the most significant discovery in astronomy wasn't just another space rock but something far more extraordinary? Recent observations of 3I Atlas have revealed characteristics so unusual that some scientists are questioning everything we thought we knew about interstellar visitors. This cosmic wanderer's behavior is challenging our understanding of what's natural in the universe. Discovery and initial detection. What are the odds of spotting a cosmic needle in the infinite haystack of space? On July 1, 2025, the Atlas telescope in Rio Hurtado, Chile, achieved exactly that, detecting a faint moving object initially catalogued as A11PL3Z. This discovery marked a historic moment as astronomers realized they had found the third confirmed interstellar object ever detected by humanity. Following the groundbreaking discoveries of 1I Oumuamua in 2017 and 2I Borisov in 2019, this new visitor was officially designated 3I Atlas, and given the cometary classification C2025N1. However, what makes this detection particularly intriguing is that despite its eventual brightness, 3I Atlas remained hidden from earlier detection due to its challenging viewing angle as it approached from the direction of the Sun. This late discovery, despite the object entering our solar system months earlier, raises questions about how many other interstellar visitors might have passed through undetected. The object's trajectory and timing suggest it may have been deliberately positioned to avoid early detection, a characteristic that has captured the attention of astronomers worldwide. Within days of confirmation, observatories globally began tracking this mysterious visitor, but its behavior would soon challenge conventional explanations for interstellar objects. Extraordinary orbital characteristics. How can an object from interstellar space follow a path so perfectly designed for studying our solar system? 3. I-Atlas possesses orbital characteristics that defy the laws of probability and challenge our understanding of random cosmic motion. The object follows a hyperbolic orbit with an extreme eccentricity of 6.14, making it the most hyperbolic trajectory ever recorded for any confirmed interstellar object. Racing through space at an incoming velocity of 58 kilometers per second, it holds the record as the fastest interstellar visitor humanity has ever detected. What makes these characteristics truly extraordinary is the object's trajectory alignment. Its path lies almost perfectly within the ecliptic plane, with astronomers calculating only a 0.2% probability of such alignment occurring by random chance. This precise positioning allows 3I Atlas optimal viewing angles of all major planets in our solar system, resembling a carefully planned survey route rather than the chaotic trajectory expected from a naturally ejected object. The mathematical precision of this path has prompted some researchers to question whether natural gravitational interactions alone could produce such an unlikely orbital configuration. Unlike typical interstellar objects that enter our solar system from random directions, 3I Atlas appears to follow a route specifically designed for comprehensive planetary observation, raising profound questions about the true nature of this enigmatic visitor from the depths of interstellar space. Suspicious planetary encounters. What are the chances that a random visitor from interstellar space would pass by every major planet in our solar system? The trajectory of 3I Atlas presents astronomical improbabilities that challenge conventional explanations for natural objects. Calculations reveal that this mysterious visitor will pass unusually close to Venus, Mars, and Jupiter, with astronomers determining only a 0.005% probability that such planetary encounters could occur by random chance. Even more suspicious is the timing of its closest approach to the Sun, which occurs precisely when Earth's position blocks optimal observation opportunities, an event with only a 7% probability of random occurrence. This strategic timing ensures that 3I Atlas remains partially hidden during its most vulnerable moment of solar approach, when increased solar heating would reveal the most about its composition and internal structure. The object's path resembles what mission planners would design for a reconnaissance spacecraft conducting a comprehensive survey of our solar system. Each planetary encounter provides optimal positioning for studying gravitational effects, atmospheric compositions, and planetary characteristics that would be valuable to any advanced civilization seeking to understand our cosmic neighborhood. The mathematical precision required to achieve such a trajectory through natural ejection processes appears virtually impossible, leading some researchers to suggest that 3I Atlas might represent something far more sophisticated than a simple interstellar comet drifting randomly through the galaxy. Physical properties and anomalies. How can an object be simultaneously ancient beyond imagination yet surprisingly well preserved? 3i/Atlas presents a fascinating paradox in its physical characteristics that, honestly, challenges our understanding of interstellar object evolution. With an estimated diameter ranging from 1 to 12 kilometers, it's significantly larger than previous interstellar visitors, making it the most substantial confirmed object from beyond our solar system. Age estimates suggest this cosmic wanderer is over 7 billion years old, predating the formation of our entire solar system by billions of years. Despite its ancient origins, 3i/Atlas has earned the distinction of being the brightest interstellar object ever observed, reaching magnitudes that allow detailed study with ground-based telescopes. The object exhibits a 29-hour rotation period with remarkably minimal brightness variations, suggesting an unusually spherical or elongated shape that maintains a consistent cross-sectional area as it spins. What puzzles astronomers most is how an object of such extreme age could maintain its structural integrity during billions of years of interstellar travel, surviving impacts from cosmic dust, radiation bombardment, and gravitational perturbations from passing stars. The preservation of such an ancient artifact raises questions about its composition and internal structure. Most naturally formed objects of this age should show significant weathering and fragmentation, yet 3i/Atlas appears remarkably intact, leading some researchers to speculate about unusual material properties or construction methods that could explain its extraordinary longevity. Comet-like features versus anomalous behavior. Why does 3i/Atlas simultaneously behave like a typical comet while displaying characteristics that contradict cometary physics? This interstellar visitor presents a confusing mixture of expected and anomalous behaviors that have astronomers scratching their heads. On one hand, the object displays clear cometary features, including a faint coma and a short 3-arc-second tail, indicating active outgassing as solar radiation heats its surface. Spectroscopic observations confirm the presence of water vapor and dust particles being ejected from the nucleus, creating the familiar fuzzy appearance associated with comets approaching the Sun. However, several characteristics deviate significantly from typical cometary behavior and challenge conventional understanding. Unlike normal comets that develop extensive flowing tails as they approach the Sun, 3i/Atlas maintains a remarkably compact and dense appearance despite its proximity to our star. The expected dramatic tail development that should occur during solar approach appears mysteriously absent or significantly suppressed. Additionally, the object's outgassing patterns don't follow the predictable models used for solar system comets, with activity beginning much earlier and following unusual intensity patterns. The combination of recognizable cometary features with anomalous behavior patterns creates a scientific puzzle that defies easy categorization. Some researchers suggest these contradictions could indicate an artificial origin designed to mimic natural cometary activity, while maintaining structural advantages that prevent the typical fragmentation seen in natural comets during close solar encounters. Scientific debate: natural versus artificial. Could humanity be witnessing the first confirmed artificial object from another civilization? This question has sparked intense debate within the astronomical community, with Professor Avi Loeb from Harvard University leading controversial discussions about 3i/Atlas's potential artificial origins. Loeb points to the statistically improbable trajectory, precise planetary encounter timing, and anomalous physical characteristics as evidence that this object might represent advanced technology rather than natural formation. His arguments center on the mathematical impossibility of achieving such a perfectly designed reconnaissance trajectory through random gravitational ejection from a distant star system. The object's strategic positioning for optimal planetary observation while minimizing detection opportunities suggests intentional design rather than cosmic coincidence. However, the majority of the scientific community strongly opposes these interpretations, dismissing such claims as irresponsible speculation that, honestly, undermines serious astronomical research. Leading planetary scientists argue that unusual characteristics can be explained through natural processes we don't yet fully understand, pointing to the complex dynamics of planetary system formation and ejection mechanisms. They emphasize that extraordinary claims require extraordinary evidence and current observations, while puzzling, don't provide sufficient proof of artificial construction. The debate highlights fundamental questions about how we interpret anomalous data and the criteria required to consider non-natural explanations. This scientific controversy demonstrates the challenges of studying truly unprecedented phenomena that push the boundaries of our current understanding. Spectral analysis mysteries. So, what happens when the chemical fingerprints of an object contradict everything we know about cosmic ice? Well, spectroscopic analysis of 3I Atlas has revealed some pretty puzzling discrepancies that, honestly, challenge our understanding of interstellar object composition. While initial observations detected the expected water ice spectrum, a more detailed analysis actually reveals significant anomalies in the spectral patterns. The observed signals rise precisely where theoretical water models predict they should drop. And this creates a scientific puzzle that's got researchers questioning their fundamental assumptions about cometary composition. This unusual spectral behavior suggests either unknown ice structures formed under extreme interstellar conditions, or maybe even the presence of exotic materials not found in typical solar system objects. The object's distinctive reddish coloration adds yet another layer of mystery, resembling asteroids from the outer asteroid belt, rather than the neutral or blue colors we usually see in pristine comets. Standard models just can't adequately explain this color combination along with the observed outgassing patterns, which suggests some pretty complex surface chemistry, likely altered by billions of years of cosmic radiation exposure. And to complicate matters even further, the active coma surrounding the nucleus interferes with spectroscopic measurements, making it tough to distinguish between emissions from the solid surface and gases in the surrounding cloud. Advanced computer modeling, which tries to separate these contributions, has so far yielded inconsistent results, with some analyses even suggesting the presence of materials that really shouldn't exist in natural cometary bodies. These spectral mysteries have prompted some researchers to consider whether 3I Atlas might contain artificial materials or, maybe even represent a type of object completely unknown to current astronomical science. Dark forest hypothesis implications. Could 3I Atlas represent evidence of a cautious alien civilization following the theoretical dark forest hypothesis? This controversial idea suggests that advanced civilizations, remain hidden to avoid detection by potentially hostile neighbors, conducting reconnaissance missions while minimizing their own exposure. The behavior of 3I Atlas, honestly, eerily matches this theoretical framework, displaying what appears to be deliberate stealth-like characteristics designed to avoid detection during its most vulnerable moments. The object's trajectory ensures it remains partially hidden behind the sun during its closest approach, when increased solar heating would reveal the most information about its internal structure and composition. This strategic positioning allows comprehensive study of our solar system while minimizing opportunities for detailed observation by Earth-based telescopes. The timing and trajectory appear designed for maximum information gathering with minimum exposure risk, resembling the cautious exploration strategy that an advanced civilization might employ when investigating a potentially inhabited star system. The dark forest hypothesis, popularized by Chinese science fiction author Liu Cixin, suggests that civilizations remain silent because revealing their location invites destruction by more powerful neighbors. If 3I Atlas represents such a reconnaissance mission, its behavior demonstrates remarkable sophistication in balancing scientific objectives with survival instincts. The possibility that we're witnessing humanity's first encounter with alien technology conducting a stealth survey of our solar system raises profound questions about cosmic civilization protocols and our place in a potentially crowded but silent galaxy filled with hidden watchers. Historical context and lessons. The discovery of 3I Atlas carries profound implications shaped by our previous experiences with interstellar objects and, the scientific opportunities we failed to fully capitalize on. The first interstellar visitor, 1I Oumuamua, caught astronomers completely off guard when Robert Warwick detected it using the Pan-STARRS 1 telescope in 2017. The object's unexpected rapid exit from our solar system left the scientific community with more mysteries than answers, particularly regarding its strange acceleration behavior that just defied conventional explanations. This missed opportunity, honestly, highlighted critical gaps in our rapid response capabilities for studying rare cosmic phenomena. The second interstellar object, 2I Borisov, discovered by amateur astronomer Gennady Borisov at his Crimean Observatory in 2019, provided a redemption opportunity that was better utilized but still constrained by available technology and coordination limitations. Mark Norris from the University of Central Lancashire emphasizes that 3I Atlas represents our most comprehensive opportunity to date for properly investigating an interstellar visitor using advanced instrumentation and coordinated global observation strategies. The improved detection capabilities of contemporary sky survey systems, combined with enhanced international communication protocols, have enabled unprecedented real-time coordination among research facilities worldwide. Michelle Bannister notes that these lessons learned from earlier interstellar encounters have truly revolutionized our approach to studying these remarkable cosmic messengers. Future observations and implications. What will the next few months reveal about the true nature of this enigmatic visitor? 3I Atlas will reach perihelion on October 30, 2025, providing the most critical observation window in its entire passage through our solar system. Following this closest solar approach, the object will re-emerge from behind the Sun in December 2025, offering a final opportunity for comprehensive analysis before it begins its permanent departure from our cosmic neighborhood. Multiple telescopes worldwide are coordinating the most ambitious interstellar object observation campaign in astronomical history, including space-based platforms like the James Webb Space Telescope and Hubble Space Telescope. These coordinated observations aim to resolve fundamental questions about the object's composition, internal structure, and true nature before it becomes too distant for detailed study. The data collected during this critical period could revolutionize our understanding of interstellar objects and their implications for planetary defense strategies. If 3I Atlas proves to be artificial, the discovery would represent the most significant moment in human history, confirming that we are not alone in the universe and that other civilizations are actively studying our solar system. Alternatively, if proven natural, the object would still provide unprecedented insights into planetary formation processes in distant star systems and the evolution of materials during billions of years of interstellar travel. Either outcome promises to transform astronomy and our fundamental understanding of our place in the cosmos, making the coming months among the most important in the history of space science. As 3I Atlas approaches its moment of truth during perihelion, it carries with it the potential to answer humanity's most profound question: are we alone? Whether this mysterious visitor proves to be an ancient comet or something far more extraordinary, it represents a pivotal moment in our understanding of the cosmos. For more groundbreaking space discoveries that challenge everything we thought we knew, subscribe to Space Facts, where the universe reveals its most stunning mysteries. So, what if the most terrifying message from the stars wasn't actually a broadcast, but an object? And what if that object wasn't just, passing through, but actually reporting back to something else out there? In 2025, officials confirmed the detection of our solar system's third interstellar visitor, an object they called 3I Atlas. But as they decoded its transmissions and analyzed its totally impossible flight path, they confirmed a fear that humanity has honestly held for centuries. This wasn't just some random rock, it was a messenger. So, let's explore this together. The impossible visitor. So what happens when a visitor from another star system doesn't just tumble through, but actually navigates? When the Vera C. Rubin Observatory in Chile first flagged 3I Atlas in early 2025, it immediately defied every known classification. Unlike our previous interstellar guests, this object showed something that, sent a chill through every Mission Control Center-controlled flight patterns. Dr. Karen Meach, a University of Hawaii astronomer famous for her work on Oumuamua, was among the first to point out that its trajectory was, quote, non-ballistic, to a degree that is simply not natural. It executed deliberate, impossibly precise course corrections. Its sheer scale was staggering. It was surrounded by this massive 700,000-kilometer coma, a glowing envelope of gas and plasma nearly half the diameter of our own sun. But unlike a comet's coma, this one didn't sublimate chaotically. It pulsed, beating like a cosmic heart with powerful electromagnetic signals at a frequency of 1.42 gigahertz. The hydrogen line, which is pretty famous in SETI circles, firing in a perfect rhythm, once every 147 seconds. As this impossible visitor carved its way through our asteroid belt with surgical precision, one chilling question began to emerge. What if this thing wasn't exploring, but was actively reporting back? When physics stopped making sense. Here's where the story honestly takes a sharp turn from scientific curiosity into a genuine threat. Most objects from beyond our solar system follow these chaotic trajectories, their paths just dictated by gravity. But 3I Atlas showed us something entirely different. Its path allowed it to drift past several planets in ways that maximized gravitational efficiency, a maneuver that reminded JPL engineers of those complex gravity assist routes they designed for probes like Voyager. When celestial mechanics experts like Jacques Lasker from the Paris Observatory ran the orbital simulations backward, they found something, well, statistically impossible without intelligent intervention. The path of 3I Atlas required navigating through dense meteoroid streams and planetary collision zones with a mathematical elegance that was honestly breathtaking. Its trajectory deviated from a purely gravitational path by a measured 0.05 arc-seconds per hour, a tiny but constant thrust that had no visible source. It moved like a grandmaster's chess piece on a cosmic board, avoiding every conceivable threat with a precision that suggested either advanced, long-term planning, or some kind of sophisticated real-time control. This wasn't just a random space rock wandering through the cosmos. It was, as some scientists began to describe it, exhibiting piloted behavior. The object that defied reality. The unsettling feeling that we were dealing with something far beyond our comprehension only got stronger when NASA, under the guidance of senior JWST scientists like Dr. Jane Rigby, pointed the James Webb Space Telescope toward 3I Atlas. The results that came back didn't just challenge our understanding, they totally rewrote the rulebook. The thermal readings showed a consistent, stable temperature of 120 Kelvin, with rhythmic heat emission patterns that pulsed in sync with its radio signals, a behavior that, honestly, just defies thermodynamics. Webb spectrography revealed materials never before seen, including hyper-reflective compounds that returned almost 99% of the light that hit them. But the most disturbing discovery was a faint, recurring electromagnetic anomaly echoing from within. This low-bandwidth frequency at 408 MHz repeated every 147 seconds, matching the exact signature of a known pulsar, PSRB 1919+21. The problem, as any physicist would tell you, was that the object had no spinning core and no magnetic field capable of generating such a signal. It looked like it was mimicking something it had encountered, or even worse, actively communicating with something beyond our detection capabilities. Two visitors, one terrifying pattern. The mystery deepened significantly when researchers cross-referenced the electromagnetic signature of 3I Atlas with archived data from Oumuamua. The comparison revealed something that honestly sent shockwaves through the scientific community. The exact same 147-second frequency had been detected briefly in Oumuamua's data, a faint 3 sigma detection that was initially dismissed as noise. The crucial difference, though, was that 3I Atlas's signal was a powerful, sustained 50 sigma detection, an unmistakable beacon. This discovery, championed by controversial Harvard astronomer Avi Loeb, completely reframed our understanding of both objects. Oumuamua had puzzled scientists, but now a disturbing pattern emerged. The evidence suggested that Oumuamua may have been a reconnaissance probe. If this theory held merit, then 3I Atlas represented something far more significant, not passive observation but active engagement. It was, in effect, the difference between a single radar ping and a fully operational surveillance system. Some researchers now theorize that Oumuamua was the lock, and 3I Atlas is the key, designed not just to observe but to unlock something, whether buried on our planet or awaiting activation in orbit. When space objects make calculated decisions. Just when scientists believed they had mapped 3I Atlas's future trajectory, the object performed a maneuver that, honestly, shattered every remaining assumption. Telescopes in Chile and Hawaii recorded a subtle but unmistakable course shift that couldn't be explained by gravity or solar wind. The object veered slightly off its projected arc, executing a 15-meter-per-second delta V that realigned its vector, bringing it 1/10 of an astronomical unit closer to Earth's orbital plane. To mission analysts at NASA's Deep Space Network at JPL, the implications were, well, alarming. the timing and precision of this maneuver implied conscious decision-making. Even more intriguingly, the maneuver occurred precisely when the James Webb Space Telescope had achieved its optimal tracking position, suggesting the object was not only aware of our surveillance efforts, but was reacting to them. This transformed 3Y Atlas from an astronomical curiosity into a potential confirmation of technologies far beyond our own. It was no longer a passive object of study, it was an active participant in a cosmic dialogue we didn't know we were having, a dialogue that was now escalating. Ancient mathematics from the stars. As if its movements weren't enough, independent cryptographers at the SETI Institute, inspired by the lifelong work of pioneers like Dr. Jill Tarter, uncovered something extraordinary. Using Fourier analysis of the pulse's phase modulation, they found precise mathematical ratios hidden within the signal, the golden ratio, Fibonacci sequences, and the first 100 prime numbers encoded in binary. These weren't just arbitrary concepts, they represent fundamental codes that appear throughout the natural universe. The precision of these patterns suggested a level of mathematical sophistication far beyond random cosmic noise. Even more disturbing, though, was the dynamic nature of these signals. The mathematical patterns weren't constant, they changed subtly, reacting to solar activity and even our own radio emissions. Most chilling of all, researchers detected a brief disruption, a single skipped pulse, that matched exactly with the moment James Webb first locked onto it. The object appeared to know it was being observed, and had responded with a mathematical fingerprint that spoke a language older than human civilization itself. Organic chemistry from beyond the stars. So, James Webb's detailed spectroscopic analysis revealed another, disturbing layer to the 3I Atlas mystery. The telescope detected complex carbon molecules on the object's outer shell, specifically polycyclic aromatic hydrocarbons, which are, the building blocks of prebiotic chemistry. These compounds, as astrobiologists like Carl Sagan have long theorized, are the precursors to life itself. But what was really alarming was the purity and organization of these molecules. Unlike the chaotic mixtures found in comets, the compounds on 3Y Atlas showed 99.9% isotopic consistency, a level of molecular organization that just doesn't occur naturally in space. The spectral lines at 3.3 micrometers, a key signature of PAHs, were unnaturally sharp and clear. Some researchers, including those at MIT under the guidance of experts like Dr. Sarah Seeger, began to theorize that 3Y Atlas might represent a seed ship, an ancient vessel designed not just to explore but to plant the foundations of life on suitable worlds. If this theory held merit, then Earth's location along the object's trajectory might not be a coincidence at all. When Earth responded to the cosmic visitor. When Earth responded to the cosmic visitor, the connection between 3.1 Atlas and Earth became, well, far more unsettling. A classified high-altitude surveillance balloon, managed by the U.S. Antarctic program, detected something extraordinary. The balloon's instruments recorded a powerful microwave burst at 23.5 gigahertz, sharp and centered precisely above the South Pole. Now, at first this was dismissed as interference, but its timing aligned perfectly with another angular shift in 3Y Atlas's trajectory. Moments after the burst, seismic stations that are part of the global seismographic network recorded ultra-low frequency rumbles across the frozen continent. These deep, resonant frequencies were a perfect 0.0068 Hz, the exact inverse of the 147-second pulses being emitted by 3.1 Atlas. The synchronization was just impossible to dismiss as a coincidence. Somehow this visitor appeared to be influencing activity on our own planet, possibly triggering responses from systems buried deep beneath the Antarctic ice. The object wasn't just passing by, it was actively interacting with Earth in ways that suggested a technological sophistication far beyond our current understanding. The Asteroid Belt Death Run. 3. I-Atlas is currently navigating through the main asteroid belt, a phase that presents honestly unprecedented risks. Unlike other objects, 3I Atlas cuts directly through the belt's core at a low 5-degree inclination, passing through a region with a particle density 50% higher than the belt's average. The object, moving at a blistering 42 kilometers per second, is surrounded by its massive 700,000-kilometer coma, creating unprecedented interactions with the billions of objects in the belt. Planetary scientists at institutions like the Southwest Research Institute are watching with bated breath. As 3Y Atlas moves through this environment with its powerful electromagnetic signature, it's creating disturbances never before observed. While a direct collision remains statistically low, its gravitational and electromagnetic effects could potentially alter the trajectories of other bodies in unpredictable ways, creating a cascading effect or, more concerningly, redirecting the object itself toward Earth's orbital path. This is a cosmic gamble with planetary consequences. Rewiring our solar system's neural network. Scientists have now discovered that 3Y Atlas's interaction extends far beyond simple gravitational effects. Its complex, dusty plasma envelope is actively interacting with the solar system's magnetic field, creating what researchers are calling an electromagnetic web effect. As 3Y Atlas cuts through the inner solar system, it could be generating packets of charged dust that flow along the sun's natural electric currents toward Earth, potentially triggering geomagnetic storms. But the most disturbing discovery is the most recent. Observations from the Allen Telescope Array show that 3Y Atlas has begun emitting a secondary signal, a lower frequency, longer pulse at 700 MHz, pointed directly toward the Orion constellation. As SETI astronomer Seth Shostak noted, a signal not pointed at us is infinitely more chilling. Some researchers believe it's calling for reinforcements. Others think it's reporting back on its findings, but either way, one conclusion seems undeniable. This was never just an interstellar rock. This was a node, a probe, a messenger, broadcasting to something else that is still on its way. The story of 3I Atlas is far from over. In fact, it may just be the beginning of a much larger, more terrifying story. The mounting evidence, the deliberate course corrections, the mathematical signals, the organic chemistry, and now a broadcast pointed toward deep space, all suggest that this object is not the main event. It is a precursor. It is an announcement that our solar system is no longer a quiet, isolated neighborhood. We may have just accidentally triggered a sequence of events that will fundamentally change humanity's place in the universe, and honestly, we are completely unprepared for what comes next. Thank you for watching Space Facts. A bombshell just dropped on the astronomical community, but it wasn't from space. While the West's most powerful telescopes were blind, Chinese observatories released crystal-clear images of the interstellar comet 3I Atlas. This isn't just about a new comet, it's about a seismic shift in who controls our view of the cosmos. This sudden pivot in the observational balance is stirring more than scientific curiosity. It may signal a new era in how we monitor these alien visitors. Let's explore this together.
Strange composition.
What if a visitor from another star system was a complete chemical stranger? That's exactly what we're seeing with 3I Atlas. This object is unlike anything that originated in our solar system. Observations so far have revealed a bizarre chemical fingerprint. Its coma, the gassy envelope around its nucleus, is dominated by carbon dioxide emissions, with a CO2 to water ratio far higher than any comet we've ever seen. Data from the James Webb Space Telescope confirm this, showing a CO2-rich coma with only trace amounts of water. For comparison, a typical solar system comet might have a CO2 to water ratio of around 10%, but initial findings for 3I Atlas hint at something dramatically different. This composition tells a story. As explained by cometary scientists like Martin Cordner, such a high abundance of CO2 suggests the object formed in an incredibly cold region of its home star system, a place far colder than our own Kuiper Belt, where even carbon dioxide gas freezes solid. The presence of irradiated ices and complex organics further deepens the mystery, suggesting its surface was battered by high-energy cosmic rays for millions of years as it traveled through the interstellar void. This isn't just a slight variation, it challenges our fundamental models of planet formation, which are almost entirely based on the architecture of our own solar system.
Telescopes go dark.
But what happens when our best eyes on the sky suddenly close, right as this once-in-a-lifetime visitor is putting on its best show? This isn't a hypothetical fear, it's the reality that just unfolded. Major observatories like the Hubble Space Telescope, the JWST, and the European Southern Observatory's Very Large Telescope are the workhorses of modern astronomy. They provided the critical data that shaped our initial understanding of 3I Atlas. But these are incredibly complex machines. In mid-2024, Hubble had to switch to a single gyro mode, a necessary fix that nonetheless impacts its efficiency and scheduling flexibility. The VLT's 4 main telescopes periodically go offline for the recoding of their massive 8.2-meter primary mirrors, a delicate process that can take a telescope out of commission for weeks at a time. Even the JWST has faced challenges with its instruments. The transcript suggests several of these key Western telescopes went offline just as the comet's activity was evolving, creating a critical data gap. This isn't just bad luck. It exposes a systemic vulnerability in a highly centralized system, a single point of failure that can blind us at the worst possible moment. China steps in. Nature abhors a vacuum, and so does 21st century science. Into this observational gap, a new power has stepped in. China. Over the past 2 decades, China has invested massively in its astronomical capabilities, a strategic push outlined in its long-term science and technology development plans. The images of 3I Atlas didn't come from old equipment. They came from facilities like the Purple Mountain Observatory and the Xinglong Observatory, equipped with modern wide-field survey telescopes. These systems are capturing both the comet's detailed structure and the background star fields with stunning clarity. This capability is set to explode with the launch of the Zhuntian Space Telescope, a 2-meter observatory with a field of view 300 times larger than Hubble's, capable of surveying 40% of the entire sky over its 10-year mission. At a time when Western facilities are dark, observers in China are providing fresh frames of the coma and tail structures. This isn't just about filling a data gap. It's a strategic move that gives them a window to exercise scientific leadership. They have seized a historic opportunity, demonstrating that their long-term investment in astronomical infrastructure is now paying off on the world stage. Data controls narrative. Here's what really matters. In science, the person with the data writes the first draft of history. By capturing and publishing the first high-quality images of 3I/Atlas during this critical window, Chinese teams will inevitably shape the scientific narrative. These initial observations become the reference points for all subsequent research. Think back to 1995, when Michel Mayor and Didier Queloz announced the discovery of 51 Pegasi b. Their data, showing a massive planet orbiting its star in just over 4 days, created the hot Jupiter category and dominated exoplanet theories for years. Similarly, the Chinese images might be the first to identify key features in 3I/Atlas, setting the agenda for the entire global community. Their interpretations, published rapidly on preprint servers like Archive, will gain significant mindshare before the formal peer review process is even complete. In a scientific ecosystem where reputation and early access are paramount, this gives Chinese teams a powerful boost, allowing them to take the lead on developing the first credible models of this alien object's behavior and origins. Data sovereignty. This brings up a bigger, more complex issue. Who owns the data from another star system? For decades, Western astronomy, particularly NASA, has championed open data through archives like the Planetary Data System. This democratic approach allows any researcher anywhere to download and analyze raw data, fostering independent verification. However, this is not the only model. The European Southern Observatory often has a 1-year proprietary period, giving the original observing team exclusive access to their hard-won data. As China's infrastructure grows, it can choose its own path. Data becomes a tool of soft power. If institutions like the National Astronomical Observatories of China control access to their 3I/Atlas data, it could create data silos, complicating the creation of a complete global picture of the comet. The decision to release the raw FITS files, the standard format for astronomical data, complete with vital metadata, becomes a strategic choice that impacts not just science, but scientific diplomacy and the very culture of international collaboration. National prestige. Let's be clear, observing the cosmos is about discovery, but it's also about power. Space science is deeply intertwined with national pride and global influence. China has long used its space program to showcase its technological prowess. The Chang'e 5 mission in 2020 returned 1,731 grams of lunar material to Earth, the first sample return in over 44 years, a massive prestige victory. Releasing key images of a rare interstellar wanderer like 3I/Atlas, especially when others cannot, is an equivalent statement in deep space science. The media narrative practically writes itself. China steps up when others falter. This resonates far beyond academic circles, bolstering national prestige and justifying massive government budgets for science and technology, creating a self-reinforcing cycle of investment and achievement. It reframes the 21st century space race as a contest, not just of exploration, but of knowledge generation, positioning China as a leader in a frontier domain, previously dominated by the West.
Infrastructure fragility.
Ultimately, the 3I Atlas incident exposes a fundamental crack in the foundation of global astronomy. For decades, the field has been shaped by a heavy reliance on just a handful of powerful, Western-funded flagship observatories, many of which are, geographically concentrated in places like Hawaii and Chile, but this model is honestly fragile. This event serves as a stark reminder that our global network for monitoring the sky is just not robust enough. It highlights the urgent need for diversification and support for projects like the Vera C. Rubin Observatory in Chile. Once operational, its 8.4-meter mirror and 3,200 megapixel camera will conduct a legacy survey of space and time, scanning the entire visible sky every few nights. This kind of continuous watch is a direct answer to the problem of missing transient events. The incident also underscores the importance of geographically distributed networks like the Square Kilometer Array, ensuring that no single point of failure, whether it's technical, political, or weather-related, can blind humanity to a critical cosmic event.
Verification questions.
New data is thrilling, but it arrives with a critical question: can we trust it completely? The scientific process is built on verification, and integrating the Chinese data on 3I Atlas isn't simple. Are the new images calibrated in a way that is fully compatible with previous data? To answer that, the global community needs the raw FITS files and all associated calibration frames, the darks, biases, and flat fields required to remove instrument signatures. Without these, it's impossible to perform accurate photometry, the measurement of the comet's brightness, to see how its activity is changing over time. Furthermore, high-precision astrometry, or the exact measurement of the comet's position against background stars referenced by the Gaia catalog, is crucial. This data is needed to refine 3I Atlas's hyperbolic orbit and search for tiny non-gravitational forces caused by outgassing. Full transparency, including sharing data reduction pipelines, is the only way for the results to be independently replicated and universally accepted by the scientific community.
What the images reveal.
So, what could these Chinese images of 3I Atlas actually show us? They are far more than just snapshots. They are dense with physical clues. Astronomers like David Jewett at UCLA, who co-discovered the Kuiper Belt, would meticulously analyze the coma for structure. A faint jet, perhaps only a few arc-seconds long, could reveal the spin axis of the nucleus and point to a specific active region. By measuring its surface brightness, one could estimate the dust production rate in kilograms per second and compare it to well-studied comets like 67P Churyumov-Gerasimenko. The transcript suggests that some releases show brightness falling off more rapidly in certain sectors, hinting at asymmetric outgassing. Most excitingly, a rapid sequence of images might capture a fragmentation event. If the nucleus were to split, as Comet C 2019 Y4 did, these observations might be the only record of it happening, providing invaluable data on the structural integrity and tensile strength of an object from another star system.
Global wake-up call.
Bottom line, this event is a shock to the system of global astronomy. It's a wake-up call on multiple fronts. First, it forces a reckoning with the fragility of our observational infrastructure. It will likely accelerate pushes for more distributed networks and formalize coordination through frameworks similar to the International Asteroid Warning Network. Major observatories will likely re-evaluate how target of opportunity time is allocated to ensure that high-priority interstellar objects get immediate, coordinated follow-up. Second, it recalibrates the geopolitical landscape of space science, forcing Western institutions to forge new alliances and advocate for more resilient, internationally managed observatories. Finally, it shines a light on the changing nature of discovery itself. It's becoming less about a lone genius at an eyepiece, and more about managing vast, complex, and sometimes fragile global systems of technology, data, and collaboration. The 3I Atlas event is a powerful case study in this new scientific reality. What do you think this shift means for the future of astronomy? Is this increased competition a good thing for science, or does it risk fragmenting our global community? Let us know your thoughts in the comments below.
Don't forget to like, subscribe, and hit the bell icon for more deep dives into the cosmos.
Thank you for watching Space Fact.